that should be good. That should work pretty well. Okay. Okay, so this review is for, no, well, that's public now. Um, this review is for this pull request right here. So basically, it was just a refactor of Terraform core on its own to improve the graph generation and execution. So Terraform has always made a graph, so kind of to draw this thing out, if this is still live, I don't know. Nice. Oh. Um, let's draw this thing out. So basically, when you had your Terraform configuration before, it always made a graph, right? So you always had like these things. Um, and basically, like this would be AWS right here, and then this would be a resource right here, and then another resource, and then maybe this was like, this is right here is an instance, and then right here is an ELB. So basically, it always made this graph so that it could walk it, and this is how it figures out it could do things in parallel, like this thing and this thing could happen in parallel. Um, and that's always how it's worked. But the prior to this commit, basically, the way that graph was generated looked like this. So this is graph.go. Graph.go is where basically you give it as input configuration, which is this thing here. A module tree is configuration in Terraform. You would give it configuration and it would make this graph, make a depth graph, which is a directed graph. And let me make this a little bigger. Basically, like if you look at this file, like you can't really see my scroll wheel, but okay, note we're on like line 49 right now. And then let me just scroll all the way to the bottom. So basically like 2030 lines of stuff. And what's frightening is that's 2030 lines of fan out from one function. So it's just this function graph that took like a bunch of options and then returned the graph. But every other function in this file was private. It would just be called by this. So you could see like to make the graph before basically, okay, so here we are initializing the graph, and then we would add the config resources, and then we would add some orphans and add the tainted ones, and like all these are private, and we would just like do all these steps. But we would do it all in this one function. And to make matters worse, the graph contained a lot of states, so we could see here. So here are the options. These are graph ops. These are the options for making the graph. And you can see like as the options, we give it the diff that we have or the state that we have. Also the providers like we're configured with. Like we give it everything. And the reason we gave it everything was because each node in the graph basically like on this thing, like if this node right here is AWS instance, it was annotated with the provider that it should call, the diff that it might have, the state that it might have, whether it's an orphan or not, like all sorts of stuff. So like you had all the information you needed on the node to do stuff with it. And we thought that was a good idea at first, but basically it turns out to be really nasty. So for example, this diff is a particular point of nastiness. So let's just take a look real quick. I need you guys to understand the pain, the reason for this refactor. So there's something called graph add diff somewhere in here. So yeah, okay, if we have a diff, then graph add diff, which was responsible for, yeah, you can see like takes an already built graph of resources and adds diffs to the resource nodes themselves. And this thing's really crazy. Basically, it goes through the diff, and you don't need to understand all this, but I'll show you in drawing form. What this thing would do is basically add all the nodes for destruction into the graph. So if we like just delete, basically like here we had AWS like instance, and when it needs to be destroyed, it actually needs to be destroyed first. So with this graph add diff would actually create the like AWS whatever, the AWS like destroy what? There you go. The AWS destroy node on top of it, and that's what graph add diff would do. But then it gets a little wonky because if it's actually a create before destroy, then what it does instead is puts it down here, um, and for the destroy down here. But that's really simple. It gets really complicated when you have like more stuff you depend on, and I won't go into how create before destroy works right now. But like basically, it could get really crazy, and this this one function was doing all of that. So you can kind of see like if destroy, do a bunch of stuff, like create the destroy node, do a bunch of stuff, like don't need to understand. But then it gets really weird right here. Like if create before destroy is enabled, then you do all this other 100 lines of weird stuff. Else, like you just do the simple stuff. And basically, the reason why this was so painful is that when we went to fix a graph function or add a feature, we would add a feature like I don't even know. Well, let's just say we added create before destroy, which is crazy. So we added create before destroy, and that ends up breaking like module inputs. Like it's some really weird, like backwards thing because we're just modifying the same graph like all in one pass, and we couldn't reason about it because basically all we could see for debugging was like the config and state that went in, and then the complete graph that came out. So we didn't know where did things go wrong. And a lot of times what went wrong is basically like a lot of times we realize that, oh, like maybe we need to call graph add module orphan depths above graph add orphan depths. And like that sort of state, like as a developer, is like a whole nother level of trying to understand this file. So yeah, so basically this is a disaster. And then the second disaster that it goes hand in hand with is this file called context.go. So context.go is, as you can see, like 1,916 lines. And context.go and graph.go are basically inseparable. You can see the context has everything. And basically, the context is what's responsible for walking the graph and executing it. And without going into sort of too much detail here, you could kind of, here's sort of how it worked. You would just do an operation like apply or refresh or something. It would make something called a walk context, and then walk. And then that's pretty simple. Yeah, the walk context is pretty simple. Basically, it would get the graph. If there isn't a graph, it would build the graph like right here. So it's doing that like, you can see it's like really tightly coupled here to make that graph. And then basically, depending on the operation, if it's apply, it creates a different walking function, which is a callback that's called across the nodes, and then it would do a graph walk. And this like g.walk is just a typical graph walk where it walks all the nodes that it can in parallel and calls this callback. And then the sort of important point is like these things like apply walk function, they're just in this file. So like all the logic necessary for how to do an apply is right here in this, I don't know, 200 line function. So basically, you know, things like do the apply, and then save the state and run all the provisioners. And again, like, oh, this is fun, like how to deal with tainted things. Like there's a bunch of what's even happening here. You know, you don't know. I mean, I don't even know looking at it. So it's like basically you have all this crazy logic all in one place to deal with this graph, which has all the state on it. So like where it's getting, where is it? When we do this apply right here, this r.info and this diff and even this instance state, is instance state, all these parameters are coming from the graph node. So it's taking the graph node, which has all the state that it needs, and then using it to do execution. And this was really hard to maintain too, because again, like we would modify this function and somehow break, like for example, we would try to fix whatever this is fixes, something with like computed attributes. So we fix something with computed attributes, and then somehow, you know, that would break tainted resources. Like it's weird. Like it doesn't make any sense. It's like, well, a tainted resource or an orphan, for example, just never has attributes because it never has computed attributes because it's just done. So fixing a bug with computed attributes should never affect orphans. Like they don't overlap at all. But in this view of the world, it does. Okay, so I think that's sort of enough motivation So let's go into like how we did this. Basically, the idea behind it was to take graph.go, which was all that sequential stuff, and turn it into a graph transform. So we'll see. Okay, so I'm not quite sure what order to go in here, and anyone's like, you should just ask questions at any time if you have questions. But basically now we've turned, you can kind of see right here, we've turned graph creation into a series of graph transformer steps, as you can see as part of this definition. And we've made graph building an interface, which I could explain later. But basically, now it's really simple. Now, if you look right here, it's like create a new graph, put some metadata on the graph, and then just go over the steps and one by one transform the graph. And you could see transform.go. The graph transformer is really simple on the right, top right here. It's basically, take a graph in and modify that graph that you just got. Return an error if you couldn't transform. And you could also, if you want to specialize, you could implement this one where you take in a vertex and you return a new vertex. And something higher level will handle like maintaining all the edges for you and things like that. So this is just a specialization of this. Like I just wrote the code that implements this to call this. But in some cases, like implementing this is a lot easier, and that way, as an implementer of this interface, you don't have to worry about how do I maintain edges and things like that. And also, you're sort of signing a contract if you implement this interface where you like actually can't modify any of the rest of the graph. You could only modify a single vertex, which is sort of a nice thing to communicate with the type system. So yeah, we have these two interfaces, and they're kind of the core of everything. And now if I'm back on the left here. If we go back to, so here's like the built-in graph builder. And this state, like you could see, there's a lot of state being put into this thing. But the difference is, and you'll see in a second here, like okay, here's all the steps. So this is basically graph.go with like things in order, like first add the config, then add orphans, missing providers, like all this stuff is in order, except you could see that now like the state that we're passing in is passed into, does anyone know on Vim how to disable this relative like thing so I could click around without it moving up top their head? If not,
Switch to Sublime.
Okay. Well, anyway, you can see like now the state is isolated. Like the orphan transformer, the thing that adds orphans, is only seeing the state and the configuration. Like it's not able to see the diff, and so you're able to reason a lot better with like how things are touching different data. So everything doesn't have access to everything. It only has access to what you give it. And you can see that most things actually don't have access to anything. Like most things don't need any state. It's basically, like orphans and things like this thing here, prune destroy transformer, like has access to the diff. That's actually the only thing that has access to the diff. So one major difference with this approach compared to graph.go is graph.go would generate the ideal graph. Basically, it would only add a node to the graph if there was a reason for that node to be there. Like it would only add the AWS instance if the AWS instance had to be made. If there was no diff or something, then it wouldn't put it in there. And the difference now with our graph is that our graph is actually a logical graph. So the graph now contains everything. So this config transformer, for example, just adds all the configuration to the graph without worrying about, do I need to do anything? It's the important point of the graph now is the graph should represent what is effectively a graph that you would follow for any sort of logic, for destroy, creates, etc. Like whether or not the logic needs to be executed, it's fully expanded for you. And let's just take a look. I think config transform is actually kind of nasty, or no, it's not at all. So here's just an example. Like here's config transformer. So what this transform does is takes the configuration, which, like I said earlier, our module tree is configuration. It takes the configuration and just adds all the things you have in your Terraform configuration to the graph and wires them up with edges So just puts the edges that it basically turns your flat configuration file into a directed graph based on the variables you use in Terraform and so on. So let me see if I have an example file. I do. Yeah, that'll work. So like here's like an example file. So this thing is flat configuration. Like it on its own, when we parse it, is just an array of resources. There's no graph yet. And what this config transformer does is adds all these as nodes to the graph, and then like realizes that this references DigitalOcean droplet.app, and then creates an edge between those. And so that is what this thing is doing on the right here. So you can kind of see how easy this is, which is basically like it's super obvious kind of. So if you look at the center of the right side of the screen, it's ranging over the provider configurations, the resources, the modules that are defined, the outputs that are defined, and just adding them to this nodes list. And then at the end of it here, we take all the nodes that we added and add them to the graph. So nothing is connected at this point. But we added everything to the graph. And then we have this sort of loop right here that goes over and calls this connect dependent function that connects all the things that are dependent, and that creates all the edges. And so you can see like this transform in itself is very simple, and we could actually, because it's its own struct and its own like interface implementation, we could test it in isolation. We could control the graph that goes in and test the graph that goes out. So with the refactor, we're able to test sort of any transform in isolation, whereas before, like when we added a feature to graph.go, you couldn't test anything in isolation because it would basically be like, well, given this state of the world, assert that this entire graph comes out the other side. And it was really hard to test the edges that way, the edge cases that way. So now we're able to control like what happens when you give a config transformer a nil configuration, what happens when you give a config transformer a module that hasn't been downloaded yet, and those sorts of things. Like we're able to test all those edge cases in isolation and make sure they work, which is super cool. Okay, another important change here is going back real quick to graph.go. Let me see. Let me go to the equivalent function here, graph add config resources. So another critical difference of graph.go versus what we do now is in graph.go, every noun in the graph was this implementation of, was this struct depgraph.noun. It was just all of them were just this implementation, and we added extra data by implementing this meta field. This meta field is just an interface, so this could be anything here. And we added like the graph nodes there, like graph node resource, which had a bunch of crap. But sort of as a result, like the graph itself was really dumb because it just was all these depth graph nouns. Like you couldn't reason about it. With this refactor, I've leaned sort of really heavily on Go's interface system. So as an example, this connect dependent thing. The way that works is, let's just go. This file's a little bit whack. Cool. So here's like graph node config module on the left here. And that is the actual thing that's put into the graph. So we don't wrap this in anything. Like this implements the vertex interface. So it implements the vertex interface, which just requires a name, which is down here on line, relative line 18, sort of down here. And as long as you have a name, then you could be a vertex in a graph. Like you could be anything else. So we just put this directly in the graph. And here's where it gets kind of cool. So we have like these two functions, dependable name and dependence on. And these are implementing an interface that I don't know where it is. Maybe it's in here. Oh, yeah, here it is. So it's implementing these two interfaces, graph node dependable and graph node dependent. And basically what it's saying is like when I have this dependable name that I implement on the left, it's saying that this resource can be depended on with these set of names. Like if there's variables that use these names, then I'm the person that they need first. And dependent on is a separate thing that says that I actually depend on this list of names. And so this one happens to implement both, but there's certainly some nodes that implement only one of these. Providers, like being one of them. Missing providers only implement dependable. Like missing providers don't have any config, so they could just be dependent on, but they don't depend on anything themselves.
Hey Mitchell.
Yep.
What's the Can you give an example of where dependable name would return more than one thing?
Yeah, I could, and it's in this file. No, it's not in this file. It's basically dependable name used to be at one string. The reason it's multiple is, oh, I know where it is. Um, Here it is. So in an expanded resource, it could be more than one because basically I'm going to write right here. Basically, like you could depend on AWS instance.foo, or you might depend on AWS instance.foo.0, and we want them to be the same thing. Like
Yeah,
if you depend on foo for some reason, then you also depend on the expanded one.
yeah,
But the reverse isn't true. If you depend on foo0, you don't depend on foo. So
gotcha.
yeah, it's basically that's the reason for that. Yeah, so basically, like you implement these interfaces, and then you call this connect dependent function that I highlighted on the right, and it goes through the graph and connects those together. And what's pretty nifty, as an example, is that so our graph we wrap this dag.acyclic graph is the low-level like graphing library, but we wrap it in a graph, and what that lets us do is when we add a vertex right here, we actually check like, do you implement graph node dependable, and we're able to maintain a hash table lookup of what you depend on. So before, just kind of like a nice thing we got, before graph.go, when it would do stuff like this, it was basically an on squared or on cubed lookup every time because we would loop over all the vertices and loop over all the vertices and find them. And now we maintain this lookup table. So when we do connect dependent, it's actually just like on across the nodes and uses the lookup table that we guarantee is correct as long as you're using these the functions on graph directly, and you're not digging into this acyclic graph. If you dig into the acyclic graph, you're just on your own. But we don't do that anywhere in core, so we're able to maintain that graph. So kind of neat. And there's like I don't know, there's probably like 15 plus interfaces that a graph node could implement that does various different behaviors. So we'll just keep sort of seeing those as they show up. So back to Graph Builder here. We add the config, then we add orphans. I don't need to go over like each transformer, you kind of get it. I think the next important thing to kind of go over, well, we have these prune steps. So like this is prune provider, this is prune provisioner, and then down here at the bottom we have prune destroy. So a key thing that's part of this graph is that it generates by default sort of the worst case graph of what, the most expanded graph it can. But we do have optimization passes effectively. Like this prune provider transformer goes over the graph, finds providers that aren't used, and then removes them from the graph because they'll just never ever be needed. So, and it's kind of neat to see like how simple that was. Like that was really a nightmare in the old one, and it's so easy now. Like this is the implementation right here. It's like 10 lines of code. So right here, I'll highlight it. Go over all the vertices. If it's a provider, see like if it implements this provider interface, that's an interface you can implement. Then we continue. Otherwise, we skip it. So if it's a provider, then basically we ask like, what are your up edges? Like, does anything depend on you? And if nothing depends on you, then just remove it from the graph. Super easy, super like obvious, super hard to mess up, and yeah, like easy to test. So like that's all that is, which is pretty cool. So we do those throughout. Like we do prune provisioning and prune destroy things. And then here's that like thing I told you about. Here's the vertex transformer. So this takes a list of vertex transforms and does them. So an important thing here is so the way modules work. So modules are effectively a subgraph. Go back to my drawing space. So if you have a module, like you would have, oops, I don't have my drawing. So like this might be a VPC module, and then maybe you have like an AWS instance on it. And in the old graph.go, what we would do is this the module node right here. If you like expanded it out to some big thing, would look a lot like this. So this would be your VPC thing, and then one attribute of it inside of it would be another graph. So it would contain a subgraph in here. We still do something similar. So in order to do that thing, what we do is is this expand transform that I highlighted on the left. So this is pretty cool. This is another like example of implementing interfaces. So you can see it right here. So this, I just commented like what did it implement. So this graph node config module implements the graph node expandable interface. And if you implement that interface, then you're given a graph builder, and you're expected to return a subgraph node. And basically, like you're responsible for expanding the subgraph. And so you just expand it, you return a subgraph, and then I'll show you why. So graph node expandable is, I see a typo, but graph node expandable, you do this. And graph node subgraph is just something that has the subgraph on it. So basically, graph node config module implements that, does the expansion right here, and then stores it in a new node that it returns this graph node module expanded thing that's private because you shouldn't make one on your own. And so yeah, it does that, and that's a graph transformation. So at some point during the graph build process, it adds the module to the config, and then at some point later replaces that module with another node that is containing the entire subgraph. And there's two types of subgraph expansion in this refactor. So there's these two right here. There's graph node expandable, which is a static expand, and then there's graph node dynamic expandable. The difference is really important. So graph node expandable nodes are expanded at graph creation time, and graph node dynamic expandable are expanded at graph execution time. And the reason for this difference is that like modules we could expand statically, but things like resources we have to expand dynamically because the count of the number of resources could be dynamic based on a variable. So basically, like resources are the only thing right now that implement dynamic expandable. But when you reach a resource and it sees it's a dynamic expandable, expands it right then, and then walks that subgraph. And for a resource, that means basically you might have count equals 5, but you have 2, so it has to increase it from 2 to 5. So you get those, or you go down to a count 2. Then you only have 2 nodes, but then you have 3 orphans basically. And this dynamic expand implementation for resources finds all that stuff. Okay, so I think, yes, we build the graph, like each transform is well documented, well commented, and you could kind of look into those if you want. But the next important step is after we build it is executing the graph. So we have, I think, well, okay, so graph walk now is a function that's on graph itself. You could see it right here. And what's really cool about GraphWalk is that it's now completely generic. Like one example is I want to use this graph library. Basically, I want to extract this stuff and use it for Packer. And it's super possible here. So like graph walking takes a graph walker, which is basically a delegate. For example, it calls like entering and exiting the graph when it walks it, callbacks. And then it does the walk. But like you could see in this walk callback that it checks for a bunch of interfaces. So if the node it's walking is evaluable, then it evaluates it. Well, evaluation is its own thing, so we'll talk about that. But here's that thing where it's like, oh, is it dynamic expandable? If it's dynamic expandable, it does the dynamic expansion right here, and then walks a subgraph right then. Or is it a subgraph itself? Then walk a subgraph. And what's pretty crazy about this, but neat, is that it could be both evaluable and dynamic expandable. So for example, the resource nodes that I talked about earlier are evaluable, and when they eval, they validate that their count is an integer. You can't validate that until execution time because, like I said, it might depend on an attribute of a resource. So if you depend on instance.private IP address, then it won't be valid, but we can't know that until it runs. So the evaluable actually validates the count, but then if that fails, that'll exit early. But if it doesn't fail, then it's dynamic expandable. But then the dynamic expand could assume that the validation took place and just expand with that assumption, which is pretty crazy. There isn't anything that implements both dynamic expandable and subgraph, but I mean, I guess that's possible. So yeah, this is like super generic and really not tied to Terraform at all. The important one is graph node evaluable. So like I said, the graph is logical. So there might be work, there might not be. But the work that should be done is defined again on the graph node. So whereas before we had context.go, which had all this logic, just sort of as a reminder, we had context.go that had like all this logic in this like apply walk function that was in context. We now took all this logic that was in these functions and put them on the node itself. So to do that, we made these graph nodes evaluable, basically. So let me show you. So a graph node evaluable is a node that is able to return an eval tree. And an eval tree is just an eval node. So like I said, interface soup here, but an eval node is something that could be evaluated. It's given a context to evaluate it, and that's kind of like a scope. And then it could return a value or an error. The value is actually not used. I've been meaning to delete it, but it requires deleting a lot of code, so I haven't done it yet. But yeah, evaluation. So basically, I'll show you an example. Let's go to like an easy one. Actually, orphan resources are really easy. So we're in this orphan transform file. The orphan transform works in a bunch of ways, but it adds these things. It adds these nodes to the graph node orphan resource. So again, that's a special type of node which represents an orphan. It implements the dependent stuff, as you can see. It requires a provider. That's another thing. But here's like graph node evaluable implementation. So how do we handle orphan resources? And to know that, you just have to go to the orphan resource node and look at its eval tree. Like that's what's going to evaluate when it reaches one of these things. So basically, what happens here is it's kind of like programming in like its own special link, like writing the AST directly. We create an eval sequence, which is a sequence of lines that'll be executed. And then we do these things. So right now, like there's this eval node called an eval op filter, and depending on the operation that's being done, it'll only run this sequence if it matches one of these operations. So if we're refreshing, then what we do is we get the provider, then we read the state out of the state file, then we refresh it using that information, and then with the results, with the output of the refresh, we then write the state. And so you can see the inspiration here was really, so I mentioned in the PR that I think that the eval stuff could still be improved quite a bit, but at its current state, it's still strictly better than what we had before. But my inspiration for the eval stuff is really to turn each eval tree basically into lines of assembly. So make these low-level primitives that graph nodes can call. And then expose those, and then use those primitives. So like get provider, read state, and then kind of like assembly. Instead of nesting them, like we use pointers and write. So you're kind of like writing to memory. Like everything just writes somewhere. So get provider writes its output to this provider output, and then we pass it in as another pointer right here. And the reasoning for that was I wanted a linear list of operations that would be executed sequentially, that you saw all the inputs and outputs in one sort of, like assembly, you see everything on one line. Like all the operands are right there, and I wanted something similar. So this is what's happening here. So you can see it's like if you read it at a high level, get provider, read the state, refresh, and then write the state. Like it's that makes sense. And a benefit is that each of these eval nodes, like write, state, refresh, or what I like to call like the assembly instructions of a node, could again be developed and tested in isolation. And you could also see like I didn't do it for this. We talked about it, but I didn't do it for the refactor. We could also potentially do like semantic passes across the thing, which is like an eval write state should never precede like a refresh or something like that. Like we could do stuff like that and figure it out. Like if we make it better in the future, we could optimize out like get provider will always return the same thing. So we could write an optimization pass that calls get provider once or something and then caches it. Like things like that are possible. Whether they're necessary is your opinion. But for this, like that's what's kind of neat about this. So kind of going forward, we can see like how do we diff an orphan? We read the state and then we call diff destroy, which always makes a destroy diff, and then we write the diff to the output. And that's very, like, eval diff destroy is very different than if you looked at the regular, I'll just open it. So the regular eval tree of an expanded resource. So here's the eval tree of a regular resource. This one's the most ridiculous eval tree of all of them, but let's see. Oh, wait. Why is it so small? I'm confused. Well, I don't know why that's so small. Oh, I'm looking at the destroy resource. Here it is. See, like, this is a program, man. This is really long. But okay, like here on the left, I have the, you can see right here, this is the what happens when you plan a resource. So you can see we interpolate some configuration, we get the provider, we read the state, and then we do a diff. An eval diff is different from an eval diff destroy. And so diff is a lot more complicated. Like, it actually calls diff on the provider, and you can see that the provider is one of the operands. So, like, maybe it's doing that. Like, if you've never seen this before, you could be like, well, maybe it's calling diff on the provider. But if you look at diff destroy, it doesn't even have access to the provider. So it's clearly not doing that. And actually, all it's doing is returning a fixed diff that says destroy it, because it's an orphan. Like, there's no other diff for an orphan. You just destroy it. So yeah, there's like a difference there. But like, the logic is isolated in these eval trees. You call these what I call assembly instructions, the eval nodes, and then you return it. And then basically back to graph walk.go, we get this eval tree right here, and then we evaluate it. So we call this eval function with a context. And so eval just walks these instructions in order and executes them, basically. And you can see the context. So here's an eval context. This is basically the scope. And this is what I call the syscall interface. So, like, again, like, following that motivation, the context for me, I wanted to make it like a syscall interface, which is this is the low-level API that evaluation nodes can access in order to do things with the real world. But the scope and power is limited, and also it gives us a point to do a bunch of logging. Armand and I, for example, have talked about in the future implementing a debugging utility in Terraform, which is like strace, which is basically all it would do is log the syscall functions that were called in order, because you can't read state, you can't write state, you can't modify, you can't get a provider, you can't really call a provider function without going through this interface. And so a cool debug mechanism would be to basically strace the Terraform run, figure out what quote-unquote syscall functions it's calling, and without knowing anything about the eval nodes or anything, we should be able to find bugs that way. We should be able to find logical issues, like the parameter to this apply or this diff was super wrong or interpolated incorrectly, and we should be able to find it here without caring at all about the graph or anything else to start. But so to start, the eval context is actually pretty broad. Over time, it would be really cool. What I would like to do is make this eval context smaller, but I purposely have like some of these pretty hammer like functions in here. I don't know, like interpolate is a pretty beast mode function. I don't know, maybe it makes sense, but I put it in here because it made the refactor easier, and that was my goal initially. So there's like 10, 15 functions in this context, but all evaluation of Terraform is made up by calling these 15 functions. Nothing else can be done. Like, you can see like diff and state have to be pulled out of here. So yeah, we have an eval context. That's what's passed into the eval nodes, and then the eval nodes, we could look at an example. Let's look at diff destroy, because that's a simple one. So we saw this eval diff destroy. So here's the eval implementation. Basically, if there's no state, then we're already destroyed, so there's no diff. We can return that. We call some hooks, and then here's the diff. Like, it's just static. It's just destroy it, and then you write it, and that's the output. Like, it's super simple. And again, you can imagine how you test this in isolation. Looking a little more complicated, here's the real eval diff function. Like, if we need to call a provider diff, so we just run diff effectively, make sure it's never nil. Do stuff like if the diff required new, or the state ID is changing, then it requires a destroy, so set that. Do this logic where if we are requiring new, then make sure we put in the diff that the ID is computed, because providers don't have to do that, so we do that for them. And then write the diff. And then also, this is an important step, is like update the state. So when we do diffing, we update the state so that interpolations work as we're doing a diff. Like pretty complicated step, but important. And again, we could test it. So like this logic is all here, all in its one place. And yeah, that's kind of all over the place. Like here's a compare diff operation, and there's a bunch. So the convention I've used, which I think you could see, so there, like I just tab completed some stuff at the bottom, is all the eval nodes are prefixed, the files are prefixed with eval underscore. So you can see that there's quite a few. Well, a lot of these are test files, but there's quite a few. But you could find all the eval nodes that way. All the transforms are prefixed with transform, so you could see all those there. And then there's basically just graph.go. Yeah, I mean, there's basically just graph.go and graph builder, but all the stuff related to graphs that aren't transforms. There are so many transforms, I didn't want to prefix them with graph. But all the stuff related to graph is prefixed with graph. And then there's just context.go, which, so the goal of the refactor was to make context.go a lot simpler and graph a lot simpler. And so context.go is now 400 lines, you can see down here in the corner. Which is quite a bit smaller than 2000, and still, like, it's a lot, but it's really a lot of boilerplate. So you can see, like, the struct for context didn't change very much, and that's because, again, like, I wanted to make sure the context API didn't change. So the context API is what all the commands call in order to do anything. So if, in theory, what I figured was if I didn't change this API and I maintained the same behavior, then I would only have to modify core, and then all, like, Terraform apply, Terraform plan, like all the commands, all the config, like everything else would work. And that has ended up being true, basically. That's what we've done here. So all the stuff is still here, but context is a lot simpler. So like the graph function just calls out to a graph builder. Input's the nasty one. We're just going to skip it. But apply, like here's the apply function. It's pretty obvious what it's doing. Acquire run, release run is making sure that two applies don't run at the same time, or two like operations don't run at the same time. And then we copy the state, we do a walk with a certain operation, we prune the state. Oh, there's a debug in there. Yeah, then we return it. Like it's I'm gonna delete this now, I'm gonna forget. It's super simple, and like plan's the same way. Plan is like there's some state juggling in here, but basically it's walk, like acquire, build some stuff that you're going to write to, walk, and then return it. Refresh is like the same. You can see the same pattern over and over. Validate's pretty similar too, although a little different. But yeah, it's a lot simpler, and the logic is all in one place. So I think that's everything I wanted to talk about. I guess Paul or anyone, do you want me to focus on anything else? Like, is there something that's not clear that you kind of want me to go into? That was sort of the broad stroke over the whole thing.
So just to restate and to make sure that, like, at a high level, I understand the differences in the graphs. So basically, previously we had the lowest level we got to was essentially a resource graph. Like that was the node level of granularity, and now we have eval node graph, and each of those nodes has its own sort of pattern that it uses, like which is almost a subgraph, but you're like more like assembly. Is that all? Is that all relatively accurate to how you're understanding?
Yeah, that's pretty accurate. Like just to like drive that home, I guess I could draw here. Cool. So like we have this graph now, and it still looks like this. Like at the end of the day, it still is pretty similar. But then, so this graph is a lot. This is the logical graph, and this graph is a lot louder than it ever was before. So let me actually just show you. So I hope I have master. I definitely have the master. So let me make this a lot bigger. Is that good?
Yeah.
Okay, so I have this example Terraform file, right? So if I do a plan, it's really annoying. Yeah, I'm just gonna fill that in. I don't need it to succeed. I just need it to run. Yeah. So basically now the plan works, but if I put a log in front of it, um, okay, you could see. So now, well, first of all, now in the logs, like we actually output the graph after each transform. So you could actually, through the debug logs, see exactly what's happening in every one. Like there's been nothing happening. But then you could actually go and here it is. So here's like the final graph that it generated. Um, and I know because root transform is the last one. So here's the final graph it generated, and that's a lot of nodes. Like it's really loud, and it's there on purpose. Like something that's new, like destroy tainted nodes are new because it was easier in this new model to just represent tainted nodes as their own special resource. I just did it. Like it makes the graph louder, but it makes the logic so much simpler because tainted nodes have their own eval tree, which is a lot simpler. But you can kind of see that it's super blown up. And so the difference between this graph and the last graph is if you, I don't have like an easy way to compile it right now, but if you ran Terraform 037 against this, the graph here would be like, I don't even know. Let's say there's 20 nodes here, maybe no, there's 10. The one over there would have maybe 4. Like it's a lot smaller, but that's sort of a design feature. So this graph that we make is really loud, contains a lot of detail, and we rely on optimization passes to go in and fix it up. And also, so then also if we, let's like dig into this node, that's an arrow. It's a really screwed up arrow, but that's an arrow. Like if we dig into this node here, then basically what it ends up looking like is we're in that node, which is now square, and then in that node there's basically the eval tree, and that's like you said, it's another graph, but it's actually not a graph. It's a sequence. So it's like a directed it's like a program, right? So it's just one instruction at a time, and then you execute it. So yeah, that's what you said is spot on. But I just wanted to drive that home.
Cool.
Yes. Okay. Let me think if there's anything else. So I guess let me walk through like what if I were to add a feature, what I would think. So there's really like a few major steps in running Terraform now. It's config parse, and then it's create the logical graph, run a bunch of steps over that, and then it's walk the graph, get the eval nodes, and then it's execute the eval nodes. So if I were to implement, so for example, I'm implementing continuous state saving right now, which is basically we want to save this partial state out persistently after every apply instead of in memory, so that if Terraform panics, then we still have a healthy partial state, or healthier partial state. And so my line of thinking with that was, I think I could go to like, what am I in right now? What is this? Oh, this is resource, huh? Yeah. So I'm in expanded resource, which is the resource eval tree. Like I said, this is the craziest one. It doesn't get crazier than this. But what I was thinking was like, well, I could basically find, there's it, like walk apply. So here's walk apply. I should be able to find this program in here, and then make it so that after, let's see, after the apply, here's the apply. Like here's write state, but write state goes to memory. So the way I'm thinking about it is, I'm not sure I haven't done it yet, so I'm not sure yet. Basically, what I'm thinking is I could either modify write state to call a hook that does continuous state saving, or I could just introduce like a new one, which is like eval persist like partial state or something, and just put it in there, and that's what I would do. I would test that in isolation, and then what I would also do is we have this context test. I'll open on the left, and we still have this context test.go, which is still like, they're basically like unit integration tests, if that makes sense. Like we get a full configuration that's written in the Terraform configuration language, and then we actually run like plan, we run apply, and then we test the output like at the end. And so basically what I would probably do is write a failing context test first, because they're all encompassing, which is basically the test for me would be, when we apply resource number 1, succeed. When we apply resource number 2, panic. And then I'll recover the panic in here, but I would say to panic it, and then test that the final state we got contained partial state for the first resource, even though we panicked. Um, and that would fail right now, and that would succeed hopefully with modifications to this eval tree. And then it's kind of like Paul's kind of familiar. That my testing strategy with Terraform is basically defense and depth. So once we get that test passing, then I would go down further and like unit test the partial state and unit test unit test the assembly like eval node. If we did graph transforms, I would unit test those. So basically just try to get the feature done first and then unit test it all the way down. So you basically have multiple layers that are kind of clear at where you would add features now. Like you're either modifying the graph with the way it does, like, does this feature require a new graph node? Like continuously writing state, I guess like one way to look at it is we could implement a graph node that then writes the state of the previous resource. Pretty jank, but like it's an idea and it's possible. And so like if we were to go that route, then it would be a graph transform with its own custom eval tree. If we were to go a custom, if we were to add a new instruction to an existing resource, then it would be an eval tree modification. And if we're like adding a new config syntax, it would be a config modification. Like it's a lot clearer now where these changes happen.
Cool beans.
Cool. I think that's it. It ended up being, I mean, it took a long time to do, but I think overall, like this will be a lot cleaner to implement stuff. Yeah. So I think that's it, unless there's other questions.
So I'd like to talk with you a little bit more in detail about like kind of upcoming features and how they're expressed into this world. I don't know if that's sort of a separate conversation.
Well, let's just talk about it in here, because I mean I think it's good to go over like how would we implement features in this new state of the world.
Okay. I mean, it's okay to talk about O4 features.
Yeah, they're gonna be public soon enough anyway. So
Yeah, then we could just kind of walk the list a little bit, which is like partial apply, like how do we express that?
okay. Yeah, okay, so partial apply. Yeah, that's a really interesting one. So partial apply, when we talked about it, so we kind of Armand and I ran through this when we were designing this refactor, and that was before you started, Paul. But basically, the way we viewed partial apply was that it would probably be a graph transform. So here's what I mean. So let's see, graph config node. Oh, this is the only weird file. Like I need to rename this file, but okay. So I'm in graph node config resource, which is a resource from the config. It's dynamically expandable, so it expands at runtime due to count. But basically, in this dynamic expand, the way we expand it is we create a list of graph transforms and we execute it. So with partial apply, what I was thinking was that we would add a new graph transform here, and the graph transform would actually prune out resources that we don't need to apply right now. So basically, like okay, I don't know how this feature is going to look. So let's say that the feature, the way it looks like, is only apply this change to 10% of my nodes at a time. That's the thing. So basically, there would be a graph transform that was given the state. It would need to know the state. So it's given the state, and then it's given that configuration, which is do it only 10 at a time, 10% at a time. And that transform would first go through and ignore the ones that are already done. And then it would go through again and find the ones that aren't done, and then only take 10%. And then for the other 90%, replace it with a no-op graph node. So that way, when the eval tree happens, it just naturally doesn't apply those nodes.
So there's dynamic expansion. There's a concept of dynamic expansion right now, but not dynamic transformation, right?
Well, it's in this case it's one and the same because like the config resource represents. Okay, I'll draw it actually. It's easier to draw. What? Okay, so a config resource right now is just like its own big thing. Like this represents potentially n number of AWS instances, but it's in the logical graph. It's just one node. Basically, what I'm saying is take that one, and when it does a dynamic expand, it turns into basically a root, which does nothing, and then it turns into let's say its count equals 4. So it turns into 4 things that need to be managed, and that's a subgraph, like a dynamic subgraph that's in this thing.
And so we're modifying the dynamic expansion of those nodes
Yeah,
to.
yeah. So for partial apply, I would say like, oh, nice, I have colors. I would say like for partial apply, I would be like, oh, this that's not green at all. Well, it's green. Um, let's say like this one's done. So okay, well let's do 25%. Count equals 25 because it's easier. So for with 4. So this one's done, but we're saying apply 25% of time, but the rest aren't done. So we can say 25% of 4. We need to change this one still. So let's keep that node in there. But then these ones, these red ones, like they don't need to be done. So instead of like, yeah, basically marking them red, what I'm doing is like, I think instead of just deleting them, it would be more informative in the graph to actually just replace these guys with, replace it with a no-op node, which is just does nothing. Like it just doesn't even implement eval tree. Like if it doesn't implement evalable, then it won't be eval. So, but that way, like we could look at the graph and be like, oh, that was replaced by a no-op,
Got it.
and we could name it, right? So if like we printed the graph out, then the name of this thing right here could be the name of the red ones, but suffixed with like ignored due to partial apply. Like that way we could see in the graph like why is that node there. That's
Um,
probably how I would do it.
that's what are we calling the other when I said partial apply, I was actually thinking about addressing a subtree. It's like I don't want to talk to the database cluster. I only want to do modifications on the app nodes or something like that.
Okay. Yeah, so that I think would be logical, right? So I
Yeah.
think that case, like I'm just gonna keep drawing on here, is
I mean,
that case you
this is still valuable to talk about. I just don't know
yeah, that
the other feature.
yeah, that case you have this, and then well, here's what's really cool about that actually is you're saying like this is what you're gonna say is like I only want to modify the the AWS instance, but let's say that modifying the AWS instance is dependent on due to your way your config is like it can't actually change your AWS instance unless it's dependent on resources are also up to date. Um, like maybe I've thought about this, and there's some case where that's possible. Like you're saying, like I only want to do okay. You do a diff, and the DNS record is changing because your AWS instance is changing. So then if you did a partial apply where like only change the DNS record, it has to be able to know that it's an error that there is no change in the DNS record because its change is dependent on other changes. so
Right.
you so you can't partial apply. It's basically like we again like given the caveat that this feature isn't designed yet, but we have to think through like is partial apply only apply this resource or is it only apply the changes necessary to change this resource?
Yeah,
um,
yeah, yeah.
and I think it's a command line flag. Like I think there's reasonable things for both. So what's kind of neat is it when in the implementation of this, here's the logical graph in the bottom left here of this thing. Like we could have the DNS. This is the DNS down here, and then this is the AWS instance right above it. And we could actually do a transform for partial apply and replace that with like some other thing, which is like don't run it. But then, oops, I lost my colors. Uh, when we get to this green puke colored thing down here, basically we could just kind of climb upwards and like easily see like this won't work because this has a diff attached to it, and that diff needs to be executed for me to do something. So the logical graph actually helps you in this case. But then yeah, if there's no changes up here in this black red one, then the green could just execute, and it's actually the same as normal. So I think it's a graph transform and then also a semantic check basically.
Sure.
And so like I think what's cool about it is it doesn't require any eval tree changes. It's just a new to graph transform and probably a second transform. Semantic checks are just transforms that don't do any transforms. So I think it'd be one transform that does it, and then another transform that goes across the graph and makes sure that that all the partial apply implementers are have a clean dependency tree in order to apply.
Yeah. Cool.
Cool. And then let's just see here. So continuous state I already explained. Partial execution, partial apply. I mean, actually, all the partial stuff is basically graph modification. So I think that's how you would do it.
Yeah.
Um, Here's another cool thing though, actually. So right now, actually, let me go to the graph builder. Since you brought it up this morning, let's talk about providers and multiple regions.
Oh, right.
So here are the provider transforms right here on the left. Missing provider transform. What that does adds provider nodes in there. Like if you didn't say provider AWS and configure it explicitly, this is what adds it to the graph. Then there's provider transformer that actually hooks up all the providers. So there's an interface that you're able to say I'm provided by someone, and then there's an interface where you're able to implement to say I provide something, and they hooks those up. It's kind of like the dependent ones, but specific to providers. And that's what this does. And then prune providers removes them. So I think like in this provider transformer, what you could actually do is add the different nodes and then just hook up um, the proper edges so that like the ones depending on the West Coast region are talking to the West Coast provider, and then it's a little bit of extra work, but then on this right side here, this get provider, we could just get it to work somehow to like return the proper thing. So it would require minimal changes, I think. I think it would just be a new transform and then modifying get provider to support somehow knowing the difference between two providers named AWS. Like I don't know how, but
Yeah, you probably have to add
yeah.
another parameter to get provider to give it a little bit more context.
Right. Yeah, that's right. That's
Cool,
what
it's
I'm
not
thinking.
in there. That's nice.
Right, but then the nice thing is that none of the other logic changes. Like as long as it gets the right provider here, everything else just works.
Right. Cool, cool. Yeah, this is nice.
Cool. All right. Yeah, I think that's it. So I'll stop the broadcast and figure out how to make this public somehow, and add it to the issue. But that's about it. Paul, I wanted to not. I kind of want to eat now,
Yeah,
but
good.
I want to go over this with you too today
Okay.
because it's gonna like the merge of this is gonna block me on continuous state. So I just want to talk to you about it, but we'll
Okay.
do it after.
Sounds good.
All right. See ya. See ya, everybody.
Thanks, Mitchell.